Okay, so let's look at the impact of a change in temperature. So changing the temperature of a chemical reaction will change the rate constant little k. I know we're using the same letters. Little lowercase k is rate constant, whereas larger uppercase k is equilibrium constant. So let's look at an example. If we have reactant A forming product B, these are our two rate laws for the forward and the reverse direction. Rate constant K times reactant A for the forward reaction. For the reverse reaction, our reactant would then be B. We'd go from B to A. So we would have K times reactant B. Now at equilibrium, these two rates are equal to one another. And if we just rearrange this, if we rearrange this to isolate K by itself, we end up with the concentration of B over A, which is equal to our equilibrium constant K, K sub C for concentration. So what this tells us, right? Recall that the rate constant K depends on temperature. We learned this in kinetics. And it turns out, right, by that relationship we just saw, that this also means that the equilibrium constant, big K or uppercase K, also depends on temperature. So in order to predict the shift in equilibrium, if we change the temperature of a system, we predict this by looking at enthalpy. We have to look at the enthalpy or delta H of a reaction. So here's an example. This is the decomposition of dinitrogen tetraoxide. The enthalpy of reaction, or delta H, is found to be positive 52.20 kilojoules. So in order to predict the shift, we treat heat as a reactant, right? Because delta H is positive, so it's endothermic. So that means the system is absorbing heat. The system is absorbing heat to progress from reactant to products. So we treat heat as a reactant. And so we could rewrite it like this, where we have dinitrogen tetraoxide plus heat yields to nitrogen dioxide. So to figure out how a change in temperature, i.e. a change in heat, will impact the system, and to see which direction the system will shift as a result in this change in temperature, we use the same method as we did when we looked at how we change reactant concentrations, right? Because heat is now just a reactant. So an increase in heat, right? If we were to increase the temperature, an increase in heat would be the same as an increase in a reactant concentration. So the equilibrium will shift to the right, right? Because we'd have more reactants. So it would shift to the right to product formation to reestablish equilibrium. Now, if delta H were negative because it was an exothermic reaction, then we would treat heat as a product. So heat would be as a product. And then if we asked, if we increase the temperature, what way will the reaction shift to reestablish equilibrium? Well, now we would treat heat as a product. So if you increase product concentration, or the amount of a product, it will shift to the left. All right. So the main takeaway here is to predict the shift of a reaction by changing its temperature, we have to consider its enthalpy of reaction. And we can treat heat as either a reactant or a product, depending on if it's endothermic or exothermic.